less show and tell and more nuts and bolts of PyTensor. So one of the key things that PyTensor does is, of course, these rewrites. And so I want to show how all that works at a very nuts and bolts level. And I want to do it with a motivating example of linear algebra. Okay, things I want to see the last one first. It's like a Quentin Tarantino movie. Okay, so there's this library called COLA, which is a compositional linear algebra. I suggest everybody check it out if you haven't seen it before. It's very, very cool. It's a JAX package that introduces
Did he die for everyone else?
Yes.
Okay. It's so good it was kidnapped. He was having a connection issue, so maybe they came now to hunt him. Okay.
Is today going to be independent of last workshop?
Yeah.
Nice. I'm still catching up on that.
It's fine. Actually, we didn't get any of the notebooks ready, so if people want to do notebooks today, it'll be from the previous sessions anyway, which I guess is opposite what you're saying, but it's simpler or more self-contained stuff. Don't know if you wrote on Discord anything. Maybe I do my side. I don't know if he's gonna ever come back from the dead. Okay, I'll share instead and do my half. Or wait, he came back.
Sorry about that. Ricardo has the notebook. Worst case scenario.
I could have, yeah. That's true. I was gonna do my side instead, but I could.
Okay. Okay, so sorry about that. So I was saying that there's this library called COLA. COLA lets you declare linear algebra primitives in JAX. So instead of saying like A dot B, or I guess a better example is solve AB, you can first say A is going to be a lower triangular matrix, and then B is going to be a vector. And so then when you call solve AB, COLA knows that, oh, okay, I have a lower triangular solve, so I can call a special routine to make that faster. And there's tons and tons of tricks in linear algebra to speed things up quite a lot. Some that we even use in PyMC. So if you work with Gaussian processes, you might know this Kronecker kernel that's available. And actually, this is just a linear algebra trick. It's saying, okay, I want to invert the matrix, which is the result of a Kronecker product between two matrices, which is going to have shape n times m by k times p or whatever. Instead of doing that, you could invert both of the pieces first, and then Kronecker the result. And you get the same answer, but it's going to be much faster because you're inverting two smaller matrices instead of one big matrix. So COLA could actually do this for you. If it says, I'm going to cron these, and then I'm going to invert it, COLA says, wait, I could do the inverts first. PyTensor can also reason about all of this. And so we're going to see how you can do this with rewrites. I'm going to do a trivial example. We're going to look at inversion of a matrix, which is diagonal. So if we know ahead of time that a matrix is diagonal, then the inverse of the matrix is just the reciprocal of the main diagonal. So we actually don't have to run it through any kind of solver algorithm at all. Yeah. So I'm just going to make a 1000 by 1000 matrix here, and it's just going to be diagonal with stuff on the primary diagonal. And so this is how this looks. I'm going to have an anonymous matrix here. I'm going to invert it, and I'm going to do this 2 ways.
Jesse, your sharing is frozen.
My sharing is frozen now?
I mean, I still see the speeding up inversion slide.
Hold on. Stop presenting. This is going great, I think. I think everybody agrees that. Okay.
Yeah, that looks more like cells.
Okay, I'm going to turn my camera off too, just in case that's the bottleneck. Okay, so I make a matrix. I'm going to invert the matrix, and then I'm going to compile 2 different functions. One, I'm actually calling the inversion algorithm. And then on the other one, I'm just going to I'm going to extract the diag, take the reciprocal, and then make a new diagonal matrix out of that. So these are equivalent. So I prove. And this is what the graph looks like. The smart one, though, is going to be like 80 times faster than the dumb one. And this only gets bigger as the matrices get bigger, because with the invert algorithm is like O(n) cubed. So as we work with larger and larger matrices, this is going to get better and better to have these types of smart solutions. So just as a side note, we do already do this. So basically, we're going to see how to rebuild some functionality that already exists in PyTensor. The only thing is the way that we do it, you have to build your matrices in a way that gives PyTensor hints about what's going on. So this is a restriction, and we'll talk about this more later. Right, so just to show you how it works, if I build a matrix in a way that PyTensor can guess that this is a diagonal, so here I'm going to invert a matrix, but I'm going to invert an identity matrix times the diagonal of X, then actually what you see that the graph that you end up with is a division between an identity matrix and the extracted diag of the X. So this is actually doing the reciprocal of the diagonal automatically. But it had to have a hint that this is diagonal. Previously, I don't know how to go back in this stupid thing. Previously, when we just had like an anonymous matrix X, there's no information here to guess that this might be diagonal, so it just does the most general thing possible. Okay. Okay, so how do rewrites actually look in PyTensor? They're not that simple. They're not that complicated. Every single rewrite essentially is going to look like this outline here. You have a decorator that tells it's just going to wrap whatever function you give and transform it into a rewrite. There's lots of different types of rewrites in PyTensor. This rabbit hole goes pretty deep, but the most common rewrite is a node rewriter, which is basically a one-for-one swap. Basically, it says, I have this node, it's associated with an op, and it has certain outputs. I just want to take that op and those outputs and swap them for another op and another outputs. And then every node rewriter takes 2 arguments, the full function graph and then the specific node that we're operating on. So the function graph is there in case you want to reason globally about the whole about the whole graph. And the node is the actual apply node associated with this target op here. So this is essentially a filter. If I put matrix inversion here, then in the rewrite stage, PyTensor is going to look at every apply, and it's going to say, do you have a matrix inverse? And if the answer is no, it's just going to carry on. If the answer is yes, then the node becomes the input argument here, and we go into the actual logic of the rewrite. So we're going to target inverse, and our objective is to take what we get in and replace it with diag of the reciprocal of the diag of the input. So we need to bring some things in. Matrix inverse is the name of the actual op that we're going to target. And then from rewriting basic, we're going to import 2 things. One is node rewriter, that's this decorator. The other is into out, which is just a helper function that does it takes a raw rewrite and it converts it to a form that actually can do rewrites. The machinery here is a bit more complicated. I don't want to linger on it, but int to out we just need in this case so that we can play around with it in the notebook. We'll see at the very end how you actually would get your rewrites to work, but in reality, you wouldn't be working with this int to out probably. Okay, and we're going to do our first rewrite, which I called inverse to diag reciprocal dumb because it's very dumb. It's going to look at the node.inputs, and because we're a matrix inverse, if we get to here, we know 100% that this node is an inverse node. And an inverse node is one input, so I can unpack the one input as x. And then I'm just going to return one output, so it's always a list of the outputs, and the one output is the diagonal of 1 over the diagonal of x. Okay, and then the type of this is a from function node rewriter. This from function thing is why we need this into out. That's going to turn it into a regular node rewriter. Okay, so we have the before graph. So I'm going to do x inverse, which is going to be, I'm going to make a matrix inverse, and I'm going to pass in x. Maybe you've never seen this before, but when you actually import, like if you look inside the PyTensor libraries, we'll have like capital letters matrix inverse. This will be the actual op. But then we'll also have like lowercase inv, which is actually creating the op and then calling it on the things that you give to it. So I'm doing that explicitly here. I'm creating a matrix inverse node, and then I'm passing as the input x here. And then I'm making a function graph with inputs x and outputs x inverse. And so here's the graph that that represents. And then I'm going to call into out to transform our dumb rewrite into a rewriter. And then I'm going to call rewrite on the function graph. And I have this verbose thing. It just tells us it's going to make a list of all the things that are being done to our graph. Because of I don't actually want to compile the whole thing. If I call pytensor.function, I will also get back a function graph, but it will do a bunch of extra stuff too. So I'm really trying to control the process step by step here. Here specifically, we'll collide with the rewrite that already exists. So I need to keep our thing really focused. Go.
So yeah, so the side note, this function is, you call function when you're really done. Like I have this graph, I'm going to start evaluating. Every time you are working with a graph outside of this specific use case, you usually work with a function graph, which is like just a tiny thing that tells the graph I'm interested goes from inputs to outputs. And it can clone it so that if you modify it, it doesn't affect the original graph. So if you are working with the graph itself, use function graph, and the PyTensor.function is really like the end use case. Now I want to start computing things. Hopefully that's a good mental picture to have.
So because I did this verbose wrapper here, we get this output, which just says that one rewrite was applied, and we rewrote. So there was a matrix inverse, and we have this rewrite called inverse diag to reciprocal dumb, and it's going to replace the inverse with this thing, alloc diag, blah, 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 true division 0. So what that's telling us is that we went to this new graph. Okay, so this looks a lot worse. Admittedly, the first one was simpler looking, but this one's going to be a lot faster. So if you look at the outer graph, so whenever you see this inner graphs and you want to read this, start by ignoring this. Okay, so just totally ignore the inner graphs, look at the outer graphs. We have a true division between 1 and x. X is coming from an extract diag. So this is the diagonal of x, and it's offset 0, so it's the main diagonal. So I'm taking the reciprocal, and then I'm doing an alloc diag. And then what's an alloc diag? It's all of this slicing logic, basically, to say I'm going to put these values on the main diagonal of a vector. So the alloc is zeros, so it's just making a 0 matrix, and then I'm taking a 0 vector and I'm adding the 0 vector to the main diagonal. Okay. And so just from this, we get the speed up that we want. So this is now down to the 400 microseconds. We're doing the fast thing. So this is really great. It was like 2-line rewrite. That's cool. Yes, that's a good point. Thank you for pointing that out. When you read these inner graphs and you see like *0, this means the 0th input from the outer graph. So it's this true division here. But this could be reused multiple times in a graph. So yeah, when you're looking for inputs, look for that star, and then you can match them up with this line here. Okay, and if we give a diagonal input to our dumb function, then we'll get back the right answer. Yeah, so if x is diagonal, then these two things are equivalent. If x is not diagonal, then we will absolutely not get the right answer, right? So if I pass a dense matrix, this is the correct inversion, but our rewrite will actually just return this. So it'll just take the reciprocals of the main diagonal. This is because it's dumb, right? We're not doing any kind of input validation. We're not checking anything. We're just like taking absolutely any input that goes into an inverse, and then we're saying we're going to return the reciprocal of the main diagonal. So we need to add a little bit of logic to smarten this up. Okay. So we're just blindly applying this diag. That's problem one. Problem two is I did this importing matrix inverse thing, and that should have maybe like popped some flags. Like, why did I do this? That's very strange. To know why, we have to do a quick sidebar into this thing called Blockwise. So Blockwise is PyTensor's way of handling VMAP, of doing vectorization over arbitrary inputs. So for boomers who took the old SAT, Blockwise is to arrays as LMWise is to scalars. We take an op, we wrap it into a Blockwise, and then it transforms it into a VMAPable version of that op. And it does it with like a core function signature. So what this says is that a matrix inverse is a function that goes from an m by m to another m by m. And then any other dimensions on the left are going to be batch dimensions. So if you just call ptlinalg.inverse, you won't actually get back a matrix inverse, you'll get back a Blockwise. So if we had targeted matrix inverse for rewrite, it wouldn't have acted on this because it's not a matrix inverse, it's a Blockwise. Okay, so just to show you an example, we could make a batched tensor of shape of dimension 3 with unknown shapes. And I'm allowed to make a function which takes that batch tensor and returns the inverse of the batch tensor, and then it will VMAP the inverse over all of these 5 times. So you get the inverse of all 5 of these. So we want to be able to reason about that. And what it means is that we need our rewriter to track Blockwise instead of tracking matrix inverse. Okay, this will also come up if you want to do rewrites for scalar ops. If you have a clever rewrite for multiplication or something, you can't actually track multiplication. You want to track LMWise and then look for LMWise multiplications. Okay, so here's a naive first implementation. I'm just going to track Blockwise and I'm going to do exactly the same thing. And I call this wrong because it's wrong. What happens is that now we're going to replace absolutely any Blockwise operation with diag 1 over diag x. Okay, that includes dots. Okay, that includes, you know, QZ, SVD. Okay, if you do some matrix decomposition, now PyTensor is just going to replace all of that with diag 1 over diag. So you might have seen these types of cryptic errors before in your PyMC models. And what it means is that you found a bug in PyTensor where a rewrite was being applied in a situation where it doesn't make sense. Okay, so what's happening here is that I'm taking an inner product of an x vector. So we pass in some vector x, and I'm going to compute the inner product. Dot is always Blockwise by default. So I'm going to apply my rewrite to this inner function, and then I get an error that it expected only 1 input, but I got 2, right? Remember that I said the matrix inverse, if we get there, we know we only have 1 input, so I can safely unpack here, but now we're targeting everything, so I can't safely unpack anymore. But PyTensor fails gracefully, so we actually get back just the x transpose x graph. Even though this error is raised, we still can carry on. So if you see this in a PyMC model, actually your model will still run, it's fine, but please open a ticket because you found a bug. So what we need to do is complicate our rewrite a little bit more. Blockwise has a thing called core op. So what we have to do is check that the core op is a matrix inverse. And if it's not a matrix inverse, we just bail. And in rewrites, if you bail out with none, then it signals to PyTensor that this rewrite is not needed, continue. So all I'm going to do is node.op.coreop. This is going to check. This is the actual thing inside the Blockwise. Extract that, do the check, and then if it's true, do the rewrite. Okay, so this is less wrong. You can see now when I call it on inverse, and remember this is the default version, so it is a Blockwise, I do get the correct rewrite being applied. Okay, and I get back that same long graph as before with the outer graph up here and the inner graph down here. Oh, that's cool. Today I learned. This is why I come to these. What's nice here is that actually now if I call rewrite on the inner product graph, I no longer get any rewrite. So nothing happened here in this verbose mode, which means no rewrites were applied, which means that we correctly bailed when we saw this wasn't a matrix inverse. And then the dprint's still the same there. Okay, but we didn't reason about the outputs. So if I try to pass the batched X into the inverse and I apply this rewrite, I'm going to get an error because this Blockwise should return a 5 by, like I guess, a 3-dimensional thing, right? It should return a stack of inverted matrices, but our rewrite doesn't know how to do that. It just returns one. Like ptdiag only operates on a matrix. So ptdiag tries to take the diagonal of a tensor, but it doesn't know what that is. So we get this error that the inputs must be 1 or 2D. Okay, so the rewrite just isn't applied. Okay, so now to fix this, we just have to use a vectorized graph. So what I'm going to do is I'm going to make an X core, which is always going to be a matrix. I'll invert this X core, and then I'll use this vectorized graph function we've seen a number of times to handle the Blockwise version. So I'm going to take the X inverse that I make here, and I'm going to replace X core by whatever the X is that we got in, which could be higher dimensional or could be the same dimension. Vectorized graph doesn't care. So now when I apply the rewrite, I get a signal that the rewrite's been rewritten, and you see that we actually get back a Blockwise alloc diag. So now everything's working the way that it should. Okay, so all of that was to get this stack of inverts, but the stack of inverts, of course, is still wrong, right? Because this input was dense, so this should be a dense matrix of inverts, but we get diagonals instead because we're still not reasoning about when should we be doing this specific diagonal part. Okay, so how can we detect a diagonal matrix? So this is going to get into like some design choices. The way we do it now is limited. We could do better, or we could do worse, in my opinion. So I'll start with kind of what I think is the worst approach, and it's this thing called tags. So in PyTensor, all variables can have tags, and the tags are arbitrary metadata. Yeah. So for example, I can make a tensor, and I can do this dot tag thing, and then dot tag dot whatever you want. You can store anything you want here. So I could say that this thing's going to have a tag, and the tag is going to be diagonal equals true. Now there's no get adder for tag, so you have to use the Python get adder tag diagonal and return false by default, and okay, it's true. If I look at X for a tag diagonal, it's false. So you can imagine, okay, I could go to all of the ops that return a diagonal matrix, and I could say, before you return it, you're going to tag this guy as diagonal. And then in my rewrites, I could expect that everything that's supposed to be diagonal is tagged as diagonal, and then look for the tag, and then apply the rewrite if I see it. It might seem nice, but there's no logic to propagation of the tags, which I consider to be a fatal flaw. Yeah. So for example, if we have an element-wise product between like an A and X, if X is diagonal, then this element-wise product should also be diagonal, but the tags are always lost. So in this case, we can't reason about this thing. Like we can't look up the graph and say like, this thing should still be diagonal. We just lose that information. It's also a hidden feature, right? I mean, did you know that there's tags? It's exactly my point. So I would not suggest that we do this solution. A better solution would be to introduce like a type op. This is what we were kind of chit-chatting about at the beginning of the call, if anybody heard. We could have, just like we reasoned about shapes, we could have a secondary we could have a secondary graph that reasons about types, right? And sort of say like, this guy is convex, right? This one is non-negative. This one is banded or topolets. And then as you do operations, each operation could kind of know what its consequences are for different tags. And then you could have PyTensor like, okay, what tag is associated with this object? So this doesn't actually exist. If you're interested in this, I would love to work on it with somebody, but fine, let's stop dreaming. So a real thing to do that we can do right now is to just reason about the inputs. So what we can do is we can say, okay, how can a diagonal matrix arise? So a diagonal matrix could arise if the data was diagonal in the first place. It could arise if we had a vector and it was passed into alloc diag. So if the thing that's coming into our rewrite is the result of an alloc diag, that's always going to be diagonal. Or if the thing that's coming into our rewrite was multiplied by an identity matrix element-wise, then that's always going to be diagonal. So we'll set aside case one because that's kind of hopeless. Like we can't know ahead of time what the user is going to do, but we can implement cases 2 and 3, right? So in our rewrite, what we're going to do is step 1, pull out the input, check if it's an alloc diag. Okay, if so, then we're good. If it's not, we'll check if it's the result of an LM-wise multiplication. Yeah, exactly. If it's an LM-wise multiplication, we'll check for exactly 2 inputs and that one of them is an identity. And then we'll take the non-identity input. And then if all of this is false, then we'll just bail. If one of them is the identity, yes. Right, because everything will get zeroed except for the main diagonal. And we always assume that shapes work. So like it could be that, right, you have like a 5x4 times a 5x5. Like our rewrite here isn't going to be responsible for fixing your dumb graph. Like if you do that, then we just get an error. Okay, so I pull out the input. Now, x.owner is going to be none if it's the first input of a graph. Yeah, so that's the case where this is the user's data. We don't know anything about it. So if there's no x.owner, we're going to bail. Then I'm going to check, is the owner, the op of the owner an LM-wise? And if so, is the owner's scalar op a multiplication? So just like Blockwise has core op, LM-wise has this scalar op. Also, if you don't know in Python, if you do like chained ands, it'll drop out on the first one, right? So even if LM-wise is false, then owner.op won't have scalar op, but we'll never actually get there because this was false. So it says like, oh, this is false, there's an and, I'm done. Okay, so if that's true, then that means we're in the LM-wise with an element-wise multiplication situation. I'm going to pull out the inputs. I'm only going to check the 2 input case for multiplication. Multiplication in PyTensor is actually variadic, so you could have more than 2, but I don't want to think about that, so I'm just going to do 2. And then if one of them isn't I, if none of them are I, then I'm going to bail. Okay, so if all of this is true, then we continue. Otherwise, I'm going to check, is this an alloc diag? And if it's not an alloc diag, then I'm going to bail, right? So I bail if it's a root, I bail if it's not an element-wise between an I and something else, and I bail if it's not an alloc diag. And then if all of this is here, then the input x was diagonal, so we can just proceed and do the same rewrite we've been doing again and again. Okay, and I have suggestively called this one inverse diag reciprocal Blockwise correct because this is now the correct rewrite. And we can test it on a couple different cases. So I'm going to make a scalar, a vector, and a matrix. Inverse diag of a vector should rewrite because this is an alloc diag. inverse of I times a scalar should rewrite because that's a 2 input multiplication element-wise. But inverse of a dense should not rewrite because we don't know anything about this. This is the root node case. So should rewrite applies the rewrite, should rewrite to applies the rewrite, and should not rewrite does not apply the rewrite. So everything's working great. And we still get this same graph we've been getting. You actually get different graphs depending on the inputs. Here, because it was just an element-wise multiplication, it's a little bit simpler. Okay. And we can make functions, and now, okay, this is how they look. So the very last thing is to register your rewrite. So we've been doing this thing with into out, which is not what you should do. What you want to do is register your rewrite and then call PyTensor.function so that it's automatically included. So there's a few ways to register. I'm going to focus on one and then just mention another one. The one that you're going to want to do almost always, if you make your own rewrite, is to use a decorator to register it to an existing rewrite database. So there are 3 most commonly used databases in PyTensor: canonicalize, stabilize, and specialize. We saw these on the first day of the workshop. And you can add your rewrite to one of these groups using a special decorator. How to choose is basically an ordering thing. Well, like logically, where does it go? And then also ordering. So the ordering is first you canonicalize, then you stabilize, then you specialize. By you here, I mean PyTensor. And I'm going to choose to put it in both stabilize and specialize. My logic is that this is not, should not be the canonical form of an inverse. An inverse should just be inverse x. So we should do it later in the graph. And I want to do it twice in case, like maybe there's something in stabilize that introduces an inverse, right? Like maybe there's a rewrite that if it sees like solve AI, it's going to turn it into inverse A, right? So I want to make sure that if that happens, then my rewrite catches this also. So that's why I do it twice, once in stabilize and once in specialize. How to do this, there's in tensor.rewriting.basic, you have these 3 registers. Just import them and then just slap the decorators on top of your function. And nothing else in here has changed. And now this is registered. We're done. Ricardo?
What does that mean?
I don't think so.
What does that mean?
Idempotent means that f of x equals f of x. After you apply it once, it doesn't do anything again.
Does it change if you rewrite a second time? If you apply rewrites?
Yeah, a rewrite shouldn't do something again in principle. Like in this case.
So you mean the rewrite would, if you call the rewrite and the rewrite itself, it would change it yet again?
Well, I guess like the rewrite process, if you do the rewrites and then you do the rewrites a second time, is it going to change anything on the second?
Yeah, so there's no guarantees. Yeah, so order matters. There's no guarantees that if you rewrite the graph first and then pass it through the whole pipeline, you're going to get the same thing than if you didn't rewrite it in the first place.
Also, you can definitely run into trouble if you have a rewrite that produces output that, again, would kind of trigger the rewrite itself again. So with the log sum x, for instance, if you're not careful, you can trigger cases like that, for instance. And so this is something
rewrite that targets
to keep in mind.
An expression that's in the output, because these rewrites are actually applied until an equilibrium, so until things stop changing. So if you have a rewrite that matches a pattern, but that pattern is in the output, like the log sum x has the stabilization where you subtract the max, but there's still the log sum x inside it. So you have to be careful and like check, okay, like you have to look outside and like, I don't think I applied myself yet to this part, so I'm going to apply. Otherwise, I'm not, because I'm going to end up in an infinite loop. And the other thing is you can have 2 rewrites that kind of feed into each other. So one is like, oh, I don't like this pattern, I put it into this form. Oh, I don't like this one, I put it back in the original one. If you have these 2, you're also going to end up in an infinite loop. At some point, PyTensor, there's a threshold and it says, okay, this has been going for too long, I'm just getting out.
There is some more formal rewrite machinery that Ricardo was playing around with these e-graphs that would give you more nice guarantees, but that kind of hasn't gone anywhere yet.
But those are really fun from the theory side for sure. So if you're interested in cool rewrite math, that's I think where to look.
And there's a collab notebook to start playing with it. I did implement the basic stuff, so it has like 5 or 6 rewrites. In general, so that's also what I was asking Jesse. What did you mean? There's a lot of like database science that we can probably also apply to PyTensor to make rewrites both faster and more clever. Right now, like there's a very trivial thing here. The decorator works to already like filter out things that are not useful. But for instance, you can imagine that maybe you could tell the decorator, I need at least these 2 ops to be next to each other, right? And that would already cut the search space even more. Like in this case, only call me on the matrix inverse if there's like an I somewhere above, and that would already trigger a lot. But at some point, you start making this meta language to just apply rewrites. So there's a bit of some kind of trade-off you have to make here. But a lot of like this is an area that if people are interested, it's really like I think where you can expand the most upside that PyTensor has over the other tensor libraries. But it's really the fact that we have rewrites in Python, which are, maybe these 10 lines of code wouldn't probably be so easy if you wanted to do a rewrite in XLA for chunks or whatever PyTorch uses. But it needs also people to be clever about it because 1, Python is slow, and 2, it's also easy things to blow out in complexity very quickly once you have these recursive, equilibrium systems.
So 2 questions in chat. One for Ricardo, I think will be quicker. Cold asked, what do you mean by database science?
There's this, I don't know if it's called database science, but there's a lot of literature on database querying. And what we are here doing with the rewrites is a lot like that. We are checking if a given, I wouldn't say an entry in a database, but a part of the graph, like basically we asking about how can we query our graph in the most optimal way? Like, can we query it quickly and correctly? And here querying or like pattern matching, right? We are asking, is there a matrix inverse in the graph? This is a kind of a database question. Or at least there's a lot of literature on how to make this kind of stuff fast or cleverly that generalizes beyond just, SQL databases.
And then Rob's asking, what makes tagging so brittle in practice? My answer is just that it's like half-baked. I guess in principle, nothing about tagging is like bad from first principles. It's just that it's this low-level, half-implemented attribute on things, and like there's no logic for propagation. There's no logic for like how do 2 tags interact. And like the system I proposed of like a type op, like could use tags, right? There's no reason, I guess, why it wouldn't or couldn't. Just that like, so PyMC, if you go back in the slides to the tagging part, I actually linked to the PyMC source code where it does use tags. And I'll pull that up quickly. So if you call like LKJ Cholesky covariance, what you get back is a raveled triangular. It doesn't store the zeros. And then it calls internally this function expand pack triangular. And expand pack triangular will create a triangular matrix and then tag it with lower triangular equals true. And there are actually rewrites in PyTensor that look for lower triangular equals true. The limitation, though, is that future developers need to know the existence of a tag called lower triangular equals true, so that if you make a new rewrite that implicates lower triangular, you actually have to go back and use it. So I guess like conceptually, that's another problem I have with it, that like the set of all tags is undefined. So if I go in to make a new rewrite, I don't know what information is there for me to access.
On that topic, I think how LLVM so LLVM has a similar rewrite logic in many ways, right? Kind of the library that's used by C compilers and other compilers a lot. And I think they have a split into analysis passes and rewrite passes in some sense. So sometimes they are paired where kind of there's first an analysis pass that adds something like tags, I think, to parts of the graph. And then there's a rewrite pass that then tries to make use of that information. So maybe something like that might also be useful to look at, but yeah.
Okay, just one last quick thing. So just to show that once you do the decorator, you can compile a function. So I'm actually going to do verbose on the function so we can see all the rewrites that get applied. And I'm going to do one thing here. I'm going to get mode, and I'm going to exclude. This is the name of the real, big finger quotes, real PyTensor rewrite that does this. So I'm excluding it so we can see ours. So the first thing that happens is we apply our inverse diag, reciprocal blockwise correct, and then a bunch of other rewrites happen. And then we get a nice graph out at the end. So just by adding the register decorator to the function, we were able to automatically get access to the rewrite. So the other way to register a rewrite, and I don't even have a full code example here because I don't want to encourage people to like think about this one, but if you have a highly specialized rewrite that kind of doesn't fit into any of these canonicalized, stabilized, or specialized categories, then you can manually register it in optdb. So optdb is an optimizer database. It lives in the PyTensor source code somewhere. You can actually import it, and it has a register method that you can dump any new rewrite that you want into the optimizer database. And you just have to pass the name of the rewrite itself, wraps, tags for the rewrite, and a position. So I just grabbed the first example that I could find. I was in the linear algebra section, and so this was one that was there. This is a rewrite only for JAX. So there's this function, solve discrete Lyapunov equation, that has two modes, and only one of the two modes is supported in JAX. So this rewrite says, if I have a certain type of solve discrete Lyapunov, I'm going to go in and change it to the other type of Lyapunov so that JAX could do it. And then I'm going to register it, and I'm going to give it the tag JAX, which is the tag called by the JAX mode. So when you say compile mode equals JAX, then internally there's a query done against optdb. As a first pass, it says, give me all rewrites that are relevant to the JAX mode. And one of them is going to be this JAX bilinear Lyapunov to direct. And I put it at position 0.9 to run it before canonicalization so that all of the graph logic will happen on the valid version and not on the invalid version. But again, this would be like a highly specialized thing, and that's something you need to worry about for if you have like a nice simplification or rewrite in mind to contribute. Yeah, so there's some notes here if you ever need to go back and have a look. So there's more resources. The PyTensor example gallery, you probably don't know this, but PyTensor has a very small example gallery that we're trying to work on building. And one of them is implementing rewrites from scratch, written by Ricardo. So a priori, this should be better than mine. And you can go through, and it covers a lot of the same content that we saw today. So if you're interested in this, I suggest it's a much deeper dive that actually rebuilds the machinery of how to do rewrites from nothing. And then the PyTensor docs also have an extensive section on rewrites and how all this works, how simplification, looping until equilibrium, and all of this. These are from the Theano days, so they're showing their age a little bit, but they're there, and I still want you to have access to them. So yeah, that's rewrites.
All right. Second part, we will rock you. So I will show some kind of, on one end, like for the sort of stuff we saw in this workshop, like trivial application of PyTensor. On the second hand is like almost everything that PyMC is about in, I don't know, 5 or 6 sections on this notebook, not, I don't know, 20 cells. And the point is really to kind of cycle back to the beginning. Why are we using PyTensor to begin with, right? And the argument we made is that once you think about all the stages you may care about in a Bayesian workflow, you'll see that PyTensor can give you almost everything, or can make it very easy to kind of switch between the phases without requiring more stuff from the user. So from a very minimal way of expressing the model you care about, we can do a lot with that. So with that in mind, I will kind of re-implement not a PyMC, like a spin-off, a fake PyMC that you might find out in being sold on the street for cheaper, just with PyTensor. Okay, so you don't need to be able to import PyMC. If you do, you still want to use it. And here is how you might. And this again, this is a design choice, and it's actually maybe the biggest divide between PyMC and Stan is how do you represent a model in PyTensor. In our PyTensor implementation in PyMC, we represent a model by, or APPL that also existed or still exists, I guess. We represent the model by just kind of representing the generative graph. Okay, so our model is something that has two vectors of data, x and y. We build a matrix of x's with ones on the first column, x squared, x cubed. So we do some feature engineering to build our feature matrix. And then we have some weights, which we say are going to be normally distributed. And we have 4 of them. And we do a very surprising thing. We dotted the x with the weights. And then we pass this to a normal, and we fixed the noise for this simple model, and we call this y. And this is our model specification. Okay. We can get not something as nice as the graph Vs, but we can get text Vs for free, because we can just call dprint on our likelihood or on our y, and we get the whole model representation. So everything I said is there. We have the dot, we have the stack, we have our feature engineering with the powers of x, we have our weights prior, and we have our constant noise. Okay, succinct, easy to share with others. Then, if you want to do the very first step of Bayesian kind of workflow, you do prior sampling. That's very easy because we just have to evaluate these y and weight variables. I'm going to do something crazy as compile a function from x data to weights and y. Now, there's a corner case. All libraries have their tricky ways of working with random numbers. We didn't touch on that much on this workshop. But the ugliest low-level version is you do this. Okay, I'll let you. I'll keep this as a puzzle. But anyway, if you do this magical dictionary and you pass it to a function as an update, random seeding will work in the sense that if you call this subsequence like multiple times, you're going to get new draws, and they are properly they have the proper entropy or whatever. Anyway, then for this function, we need to create some x data. Because we are PyTensor hardcore people here, we'll actually not use NumPy. We'll call pt.randomUniform, and we'll evaluate to just get some x's quickly. And then we'll pass them to our fancy prior function. We'll get weights and draws from the prior of the weights and the y. And here I'm doing a scatter plot. Okay, so we got 20% of PyMC re-implemented by doing the pm.sample prior predictive. You could wrap these in RV's inference data, and then you would trick most people. But we just keep the draws as NumPy arrays. Then this, for our purposes, because I don't really have data here, I'm going to make fake data. But I was not really happy with just the prior draws from my model. My model has very diffuse priors. I actually want a bit of structure. And in fact, I want to specify the weight. So I want to take draws, but I don't want to from y, but I don't want to take draws from the weights. I want to fix the weights to something. So let's say I would want no intercept, 0.3 for the linear term, -1 for the square, and 1 for the cubic term. And I want to take draws of y conditioned on these fixed weights. Okay, that's also very easy because PyTensor function has this thing that at first seems very annoying. That is, you have to specify the inputs when you care about some output. The nice thing is it allows you to specify things that you might not think as input. So you can specify actually an intermediate variable as an input as well. So I literally say, instead of having a function from X data to weights and Y, I want a function from X data and weights to Y. And now whatever weights was in the original graph doesn't matter anymore. Now it's an input to this function. And here in this notebook, and that's why I'm calling it partialing. Like you can think of, we have a function of Y that's going to be partial on some values of weights. I didn't specify them yet, but I could have also. No, let me not say that. And now I'll update magic dictionary just for Y. And now I can say, I can take draws from Y. I'm calling them fake in the context of like fake data simulation, where you might want to check if your library that we are building here actually works well. Is you control how the data is generated, and then you see if the inference comes back and finds out something that agrees with your the way you fake the data. So we fake Y's given these specific weights. And now we get something that's a bit nicer. It's supposed to have a subtle bump here. If there were more draws, you would see it. And then it blows up as you go to infinity. So at this point, we have data, both X and Y. And now we'll implement, let's say, 90% of the utility of PyMC, which doesn't add up with the other 20%, but doesn't matter. Posterior sampling. And I'm going to, because this is a new library, it's going to be a very constrained ability to sample posteriors from models. It's going to expand in the future. On the other hand, it's going to give you the best sampler that exists out there in the market. Right? It's going to beat NumPy by orders of magnitude, perfect effective sample size, perfect mixing, because it's just going to do conjugate posterior for our linear regression model. And most of the logic is just to tell the user that if it's not a linear regression model, we actually didn't implement a sampler for it yet. So we just do a bunch of things that I'll come back to later. But since this is provided by the user, we can get posterior draws from the posterior weights. The signature is a bit less nice than pm.sample. You can think that this is kind of, at least the first part, is the extra bonus you get from wrapping things in that weird object called PyMC model, is that you get the mapping from some stuff to some stuff. Here is very low level. The users are going to have to do it. So they're going to have to tell us what are the unobserved variables. They're going to have to tell us what are the observed variables. They're going to tell us what the data inputs are and the data values are for this specific inference. And then they can tell us tune, chain, and draws. Again, because we have a very good sampler, we don't need tuning. Chains is just so we make RVs happy later. And we'll get 100 draws because I heard that you only need 100 effective sample sizes to do most things. So that's what we'll do. And this is already posterior draws. Okay. We'll get back to that later. And we'll just check. We can use RVs. RVs is backend agnostic. It doesn't care what PPL library you use. So ours will work out of the box. It's a bit weirded out by the fact we have a single chain, but we can ignore it, just a warning. So we can see we get draws from our weights, which was like 0 should be 0, 3, -1, and 1. Very nice effective sample size above the 100 draws we asked, both for the tail and the bulk. And we can get the plots. Doesn't look very wiggly just because you are used to seeing 4,000 draws here instead of just 100, but it's, I think, a good caterpillar graph, and we recover the parameters. Now, for the part that I actually asked folks whether they were interested in this notebook or they would be interested in exploring something else, was how do we use a PyMC model? And I'll let you believe that the way we implemented the model is basically a PyMC model, where we have something like this. How do we grab a model, use posterior draws, and now make some interesting optimization on the original model? And you won't be surprised by knowing that we're going to build basically a function from something to something with just a tiny bit of work in the middle. Okay. So what I'm going to do is, for optimization purposes, I'm going to work like in expectation. So I'm going to ignore the y, and I'm going to work on the mean of the y. Okay. let's say I want to optimize something about the mean of y. I'm going to pick the first entry. Doesn't matter, could be the last one. So I'm going to pick one because for the purpose of optimization, I just care about optimizing one specific x, not a vector of x's like we had originally in our data. And this here is a bit silly in this specific model, but I wanted to put it because for very complex models, these together with the kind of the machinery that we talked about in the first session, I guess, allows you to reuse a graph and almost, or in most cases without any extra work, end up with as good as a graph as if you had re-implemented the model, just exactly the same thing to just work on one single observation. Okay, because it's going to do this fancy thing of lifting the indexing operation closer to the inputs. So for instance, we had the dot between the whole vector of x and the weights, and you're just going to do that for the one entry of x. So we're going to do that, and the way we do is just we say what we are interested in, then we're going to vectorize the graph to work with the batch posterior draws we have. So the variable I care about, and I'm going to replace the weights that still exist in the graph of the location by the posterior of the weights. These are constant. PTS tensor, if you pass an NumPy array, you're going to get a constant. So our vector weights now we replace by something that has shape one chain, 100 draws, and 4 weights. And we rely on the vectorize to just give us the correct expression, as if you're looping through all the possible weights or pairs of 4 weights. This notebook will be, I think it's already in the repo. So if you are interested in how these things look, you can uncomment this deprint, but we already saw many of those. I'm going to spare you. So once we have this kind of vectorized graph that represents kind of the location for one given day for all the posterior weights, we can start building our optimization stuff. So for the loss, I'm just going to take the mean of this. I'm going to take the gradient. I'm going to compile both the loss and the gradient. If you did the solve notebook, this is just a very trivial application of PyTensor graph for optimization. There's much more fancy stuff there in that notebook you can explore. I really suggest, so this is something I see people who do a lot of advanced PyMC stuff, but then doesn't work, or they get surprised by weird results. Is sometimes all you need to do is kind of compile a function and evaluate it to see if it's doing what you want it to do. Even as simple things as like, is it returning something with the right shape, things like that. So for that purpose, I actually, I'm not immediately passing the function to SciPy minimize. I'm first just going to evaluate it a few times. So I'm going to try a range of x's. I'm going to call it, and it has some shape that kind of agrees with the data. So I can believe that this might correspond to a mix of the data and the posterior of the weights. If it's the first time, I would suggest we even compile the function of this before we take the mean and make sure it's broadcasting in the right direction. So you're getting something that has shape one entry of log and then extra batch dimensions of chain and draws. Here I just did it for the loss. Yeah. I guess should I have negated the loss? I don't know. No, for this purpose doesn't matter. Okay. And we get something like this. Obviously, it's a single function. So our minimum is going to be 0. We can confirm that. We'll call minimize. I'm actually doing the dumb one and call the general minimize, whereas scalar minimize would be better here. I'm doing that trick that Jesse mentioned. If you set Jacobian to true, PyTensor knows that SciPy will expect your function to give you both the loss and the gradient with respect to the thing you are optimizing. And I'm setting an initial x, and I'm setting some bounds on x, and we find out that converges to something like 0. Then I just have a funny story that, we are doing some marketing optimization, and this tells us that we should spend 0 money on marketing, but that's not good because then we are out of business. So we'll just nudge the results a bit and find something between 0.3 and 1. And in 8 draws, it finds 0.42. Okay, that's fun. We can live with that. We'll say that's how much budget we should allocate. And then because we are Bayesian, and we are not just happy with optimizing something in expectation, we still want to bring some uncertainty back. And so we might want to implement the last piece of PyMC that we didn't see here, which is the posterior predictive sampling function. And you'll see again, it's just 3 lines of code. So to do that, we grab our y now instead of the location of y. And we're going to vectorize that with the posterior of the weights, so that we only have to call it once, because vectorization is all the fun these days. Again, we do this magic updating, and we compile a function from x data to our y prediction. And here I'm just kind of squeezing away, because I know I have a single chain and I have a single location point. I'm just squeezing those away by doing the 0, 0. And here, then I'm taking, basically I'm trying for every x between 0, 3, and 1. I'm calling this function, which is going to give me now draws of y for these 100 sample posteriors we had for the weights, and the specific x we passed in. Then I'm just plotting that and color coding, and we can see that for this range, we have a bit more uncertainty for lower values of x than for higher ones. And we can show both, this is the point you optimize in expectation. This is the uncertainty that you can reasonably expect around that point. And yeah, that's it. I would say that you kind of implemented the PyMC 01 that only samples one kind of model. Obviously, our sampler is not generic. We can look at it. But everything else besides the pn.sample is just not doing much more than what you saw here. And also this optimization thing that doesn't exist in PyMC, but exists now in PyMC marketing. If you do optimizing on an MMM model, is going to be doing something very similar to this. Namely, vectorize, like picking the variable you care about optimizing, and then vectorizing it with the posterior draws, doing some rewrite so that that vectorized graph is clean, and then building you automatically the functions, the loss and the gradient functions, and also constraint functions and things like that. Again, with the nice thing being the user did not have to tell us any extra code once they specify the model for us to be able to do all these steps: prior predictive, posterior sampling, optimization, posterior predictive, things like that. Yeah, I think that was it. I don't have to sell you guys on PyMC, but maybe I had to sell you on PyTensor. And this was a bit showing the bit of the heavy lifting that's happening by this library, and that you eventually have to work a bit internally once you go out of kind of the comfort zone. I'll just close by, so if you have any questions, feel free to ask them. I'll just close by looking at this posterior sampling function. Just, it's a nice reminder, or maybe not nice, a nice reminder of, how you can kind of reason about a graph, in this case, a very verbose and dumb way, and it must also be a reminder of why you hate anything related to PyTensor, is because you hate these kind of things you see here. So sample posterior, I'll start from the end as we should always, does conjugate posterior sampling for closed form linear regression with normal likelihood and I guess it matters, and normal priors for the weights. So the posterior draws are just a draw from the multivariate normal with a given mean and covariance, and here is where we put our tune and chains. Then we just slice away the tuning because there's no need for conversion. But this is kind of, if PyMC was able to do conjugate posteriors, it would probably be building something like this. Then we have an expression for the mean and the covariance. It may be correct or not. I copied this from a notebook, and the output seems to be sensible, and it seems to involve more or less the things it should involve. Basically, you need an expression for the covariance of the posterior multivariate normal and the mean. And before that, it's just kind of graph validation. And now it's just, do we actually have a graph that corresponds to a linear regression? And here I'm putting it in the dumbest way. This is not how I would implement a conjugate to kind of pattern matching. But whatever you implement in the end is going to have to be rewritten or transformed into something like this, because this is what the PyTensor graph looks like. So this is starting from the low level, and you can use your imagination to think about what would you like the API for someone to just doing pattern matching to look like. So first thing I do is just I check the number of variables. We have an observed variable, one observed. Side note, one nice thing about re-implementing PyMC is that we can use proper names for things instead of silly basic RVs and free RVs with a capital R or things like that. So no capitals in the RVs here. So I check you have one unobserved, and two sets of data. Once I have, otherwise I say this is yet not implemented. You might open an issue to implement your model. Then I check I call the unobserved W and the observed Y already in the expectation that I'm in a linear model. I check if the Y is a normal variate by doing instance Y under up normal RV. If not, there is an error. I check the same for the W. Once I know Y is a normal, I can extract the location and the scale parameters. There's a helper in the random variable op called distparams, where you pass the node itself and it gives you back the parameters and ignores the stuff like the size, the RNG, and I guess that's it these days, or any extra thing that might exist that are not really parameters. Then I check that the scale is a constant, because I didn't bother with the case where this might come out of, I guess, an inverse gamma or something that also has a conjugate posterior. So you can check a variable is a constant, or I'm nicer, and I also allow the user to pass a scalar constant that was broadcasted with the mean. So I check, is there a dim shuffle, and the input of that dim shuffle is a constant. If it's not either of these cases, I get out, because it's a non-constant noise. So this is one example where you might start to think like, there must be a better way for us to ask if something is a constant, right? Than having to check all the possible kind of operations you might have on a constant. And indeed there are, but I leave those for you to muse. Then once we know we are in this case, we first check, does the location come out of a dot operation? From Jesse talk, you already know this might be limited. Maybe we should look for a blockwise of a dot. And that's another thing to ponder. Can we have a nice way to just probe whether, regardless of whether it's in a blockwise or not? But anyway, if it's not a dot, we get out. Otherwise, now we know we have two inputs to the dot, A and B. And we have to find out which one is the weights and which one is the free random variable. So we check, is A the free random variable called W? In that case, the data, which is called phi in that blog post I stole this from, is B. Otherwise, is the B variable the weights? In that case, phi is A. Otherwise, we raise an error because there's something we didn't quite understand about the graph. Then the last thing is to just check what was the prior for the weights variables, what was the location of the scale. I use again these parameters. And then we have to still find out of the two data the user passed, because we try to be nice for the user, which one is X, which one is Y. Whatever is in the graph of phi should be X, and Y shouldn't be in the graph of phi. And then we use this, I guess we didn't show this in the notebook, but there's a function in PyTensor graph called ancestors, which gives you all the variables that lead up to a node, all the variables you need to compute if you were to compute this node, or a set of nodes. You have to pass a list or a sequence. I store those, I convert that to a set, and then I iterate and I basically ask, is X in the set of phi and Y not? And I do the reverse case. If the two cases not apply, I raise an error. Otherwise, by this point, I already know what's X and what's Y. Okay, and once I have that, I can use, I don't need X for here, I need Y. Y shows up here. And I need X to evaluate the function in the end. Although these I could just have passed the dictionary that the user gave. I only actually needed to know what Y was. And this would be a great use case of tags. What do you have in mind, Will? If you're still here.
Just a joke.
Just a joke. Don't joke. This is a serious presentation, man. That's it. Yeah. So I cheated a bit here by only using random draws. Obviously, a general sampler is going to have to use probabilities, but we touched a bit about that. That would be a PyMC workshop. PyTensor doesn't do any probabilities. It gives you both random variables and tools to work with them. And general, if you want to build general graphs, of which log probability graphs are one case. Yeah, that was it. Don't know if you guys have questions. Hope this was a bit useful. It's probably better for you to just peruse the notebook at your own leisure instead of me scrolling frantically up and down. And hopefully it just makes you, if there's something you want to do with the PyMC model, once you believe a PyMC model is little more than this, or maybe, okay, little more than these and some of these, and this mapping, saying what is what, you should hopefully free your imagination to now do whatever you want once you have this kind of graph for whatever use case it is, and not be constrained about, the PyMC label.
Maybe another side point that's not totally obvious is that Ricardo showed how any graph node can become an input. So if you call PyTensor.function, you pass the weights, it sort of chops anything that is derivative of the weights and just says like, fine, I'm making a new variable of the same type and the same shape, and you have to tell me what it is. You can do the same thing with the outputs, right? So when you have a PyTensor model, you have several different values in there. Maybe you have a deterministic halfway through that you're interested in working with, or you do like a secondary model where you rebuild your graph and you want to add some more computation. You can always call compile and take any of the variables from your PyTensor model and pass that in as the output, right? And sort of ignore all of the downstream computations or ignore any of the like complicated log P stuff that's maybe going on under the hood. So it's a way to sort of take pieces and reuse them in creative ways.
Yeah, so a trivial thing you can do is just compile a function that computes the deterministics of your model. Maybe you didn't store those for memory purposes, and now you need those. You can just set an intermediate variable as the output, right? There's nothing about a variable ever that says I'm an output. And similarly, in the same vein, there's never something that says I'm an input other than root variables, because I cannot know what their values are going to be. But other than that, you can imagine they're just there in the graph, and you can say I want to work from A to B. And that's the signature of function, and that's also the signature of that function graph that Jesse showed. That's the point at where you say, this is the subset of something I'm interested in. Then, yeah. At some point that was called like environment. And I guess function graph is a bit better name, but that's the point where you go from just a mess of nodes to specifying in and out. Until then, they don't really exist as other than, something comes before something else, because we build this as a cyclical graph. Cool. So that was the end of it. This notebook and Jesse's are already in the workshop. Then for the part where everyone except Will and Colt always bail out, we have, no, Adrian also stayed last time. We have not done notebooks because we got out of time. we were working on other stuff. But there are two notebooks from previous sessions that were not touched, and I will just propose those to you if you find them interesting. If not, we can just keep it short or chat about other stuff. I'm also happy to do that. I'll stop the recording now. If I find out to do that. Recording. Stop.